This slide contains a summary of some of the key concepts in stability that we've been developing. On the left-hand side we have firstly static stability. Static stability asks, what happens to a parcel of air if we give it a small perturbation? If after a small push it returns to its original level, it's statically stable layer. If it remains at the level we push it to after the initial push, then it's neutrally stable. And if the parcel continues to rise after a small perturbation, then it's statically unstable. At 500 hectopascals we can measure something known as the surface lifted index, which is the difference between the parcels, that is the cloud parcel's temperature and that of the environment. And if it's negative, then the parcel is buoyant. So surface lifted index is a measure of instability. If the cloud does not contain the minus 20 degrees Celsius level, there will not be sufficient ice crystals to initiate charge separation and the electrification of the cloud. So the cloud's only a cumulus with showers, but if it does contain the minus 20 C isotherm, then electrification can occur, and we refer to a thunderstorm associated with a cumulonimbus. The equilibrium level, or the level of zero buoyancy, is the region where a parcel now returns to the environmental temperature. Although for thunderstorms, you can get overshooting tops where momentum carries parcels of air through to an environment of negative stability. In the middle is illustrated latent stability, which asks the question, if we give a sufficiently large lift, will we get a parcel of air that becomes unstable after that large lift? If we do, that's latently unstable. And again, if we don't, it's latently stable, or if it remains at the same level, then it's neutrally stable from a latent point of view. And finally on the right we can see that between the surface and the level of free convection, a parcel is cooler than its environment, and so that area bounded by the parcel and the environment is the convective inhibition, which is the amount of energy we have to put into a system to realize the convective available potential energy, or the CAPE, which is the area bounded by the ascending parcel in the environment between the level of free convection and the equilibrium level. And that convective available potential energy is related to the maximum potential updraft speed, and hence various measures of severity of a thunderstorm.